Today what we're going to be talking about is understanding balanced chemical equations, complete ionic equations, and net ionic equations. So we have this word problem: sodium phosphate reacts with silver nitrate. And we know that sodium phosphate is a compound and that silver nitrate is a compound. Anytime we are starting with a compound and a compound, this indicates that we are dealing with a double displacement reaction. We can write the formula for sodium phosphate and silver nitrate, and because we know it's a double displacement reaction, we can predict that the products are going to be sodium nitrate and silver phosphate. The reason why we know that we can predict that these are the products is because the positive cation from one compound combines with the negative anion of the other compound. So Na plus combines with NO3 minus to form NaNO3. The same can be done for the second compound. We know that the positive cation Ag plus has to combine with the negative anion PO4 3 minus to form the compound Ag3PO4. We can predict the states of matter of these compounds by looking at the solubility rules on the NCDPI chemistry reference table. So we know that Na3PO4 is aqueous, AgNO3 is also aqueous, NaNO3 is aqueous, but Ag3PO4 is a solid. We can also balance this reaction by putting the coefficient 3's in the places indicated. When we write a chemical formula in this manner, this is called a molecular equation or a balanced chemical equation. Even though we write our equation this way, this really doesn't show us what is happening when we combine these substances together. And so that's what I'm going to be illustrating here. We have two substances that we're starting with, Na3PO4 and AgNO3, but we have three AgNO3s that we're going to be adding to our beaker. We know that anytime you have an aqueous ionic compound, that when you put that ionic compound into water, or when it is aqueous, the substance breaks apart into its individual ions. So when you put Na3PO4 in a solution, it actually looks like 3 Na pluses and a PO4 3 minus just floating around in the water. The same idea is true when you're looking at AgNO3. One AgNO3 will break apart into Ag plus and NO3 minus. A second AgNO3 will break apart into another Ag plus and NO3 minus. And the third substance will also break apart into its ions. So when you are putting a ionic chemical compound into water, it's going to break apart into its individual ions. As these ions are floating around in the water, they'll bump into each other. So when Na and NO3 minus bump into each other, they do not form a solid, they remain aqueous, so that means that they remain as their individual ions. But when Ag bumps into PO4 3 minus, it forms a solid. And we know that it forms a solid because that's what our solubility rules on our NCDPI chemistry reference table tell us. So when Ag plus, 3 of them, and PO4 3 minus bump into each other, they form a solid. And I'm going to represent that solid by drawing the Ag3PO4 all together. And I'm also going to show that this solid is going to drop down to the bottom of our beaker. what we have represented here is our complete ionic equation. So this was our original equation, and this is our complete ionic equation. You'll notice that in our beaker we have 3 Na pluses, we have, we had our PO4 3 minus, we had our 3 Ag pluses, and our 3 NO3 minuses. When our reaction actually combines, or when our solid actually combines, we still have 3 Na pluses, we still have 3 NO3 minuses, but we've now formed our Ag3PO4 solid. You can use this illustration to help you write your complete ionic equation. The other type of equation that we use, or that we write, is something called a net ionic equation. The net ionic equation is only concerned about how a solid is formed. So when we look at what makes up our solid, the only things that make up our solid are the Ag pluses and the PO4 3 minus. So if we were going to write the net ionic equation for how we made that solid, we would say PO4 3 minus aqueous plus 3 Ag plus aqueous gives us Ag3PO4 solid, and this is how we would illustrate what's happening in the beaker.